Here's the interval 0, 1. And I'm going to define the Dirichlet function. The Dirichlet function is 1 if x is rational, 0 if it is not. Okay? Now, a common trick in calculus books is to have all the partition subintervals have the same length. So they would take, e minus a over n. Instead of having random lengths here, they would have them all the same. So if I do such a partition here, I ask you, are the partition points going to be rational or irrational or a little of each? They're going to be what? They're all going to be rational, aren't they? They're all of the form k over n, where n goes from 0 to n. K goes from 0 to n, right? So if we do the Cauchy integral, we're going to get these heights, aren't we? As they're rational. And then if we take the base here times that height, base, that height, base, that height, what's the Cauchy integral of the Dirichlet function going to be? 1. But it's not really, is it? It's 0. So you can make a big boo-boo by not paying attention to the definition. The Cauchy thing requires it to be any partition. Any partition. And of course, if you picked a partition that had all irrational partition points, you'd have 0. The thing is that there would be partitions that would satisfy the norm criteria that would give you an integral of 1 or sum of 1, and then some that would give you 0. So the limit that we're asking for in the Cauchy limit definition, Cauchy integral definition, wouldn't happen. You'd be stuck. Some partitions, even if you picked a tiny, tiny epsilon and a tinier still delta, you can never get the partitions to behave. There are partitions that are arbitrarily fine with arbitrarily small norm that will give the sum 1 and some that will give the sum 0. Never the twain shall meet. Integral doesn't exist. Cauchy integral of the Dirichlet function is a mirage. Okay? But if you do the calculus book sort of regularization of the subintervals, you can easily fall into the trap of thinking, hey, I think I just agree with it. Really, right? Okay? You okay with this stuff, Matt?
Yeah.
Okay. All right. All right. So that's a little bit about that subject. Okay. Now, I know in our book in chapter 1, the next integral they talk about is the Riemann integral, but I would like to talk about the Darboux. Because, first of all, the Darboux formulation is exactly equivalent to the Riemann formulation, and it's probably easier to understand. This is the idea. Well, let's read that, and then I'll do it on paper. You have a function defined on AB, and you have a partition. And for every subinterval, you go and find the int and the sup of the function on that subinterval. The ints are the lowercase and the sups are the uppercase m's. Okay? And then you basically you create a lower sum, which is all the rectangles that are strictly inside, and an upper sum, which is all the rectangles that are strictly outside. Right? So a rectangle that's in the lower sum is going to be totally under the function curve. A rectangle that's in the upper sum is going to go completely past it and contain it, be on the outside. It's not like, it never crosses over. Because it's the sup, in that subinterval, you go all the way outside. Because it's the int, you go all the way inside, right? Okay. So you've got a stack of integrals that's just inside and a stack of integrals that's just outside. Rectangles that are just outside. Okay? Rectangles inside, rectangles outside. Add them up. Now, force the partition norm to go to 0. What happens? Well, as you add more partition points, I'll draw this in a second. Here's what does happen. As you add more partition points, a lower sum has a chance to come up. You know, because you now say this particular rectangle and he's a little bit depressed down here because there's a piece of the function graph that goes way down. And suppose you just put another partition point and now there's a half of that rectangle is low, but the other half is allowed to be a little bit taller because he's in a different place, right? So the lower sums come up, the upper sums come down. Okay, so you take the supremum of the lower sums and the infimum of the upper sums over all the partitions as the norm of the partitions go to 0. If you do get convergence there, if the sup of the lowers and the infs of the upper, the inf of the uppers, say that fast, converge to one value, you say that is the Darboux integral of the function of the intermediate. The inf over all the partitions available of the lower sums is the lower Darboux integral. That's the one that has the bar downstairs. The sup, did I get that right? I said the sup of the lower. The inf of the upper sums is the upper integral, written with a bar above the b, integral a to b, written with a bar up there. And the two things that are equal, if the function is Darboux integrable, are the upper and lower Darboux integrals. They may exist separately, but they may not be equal. In the case of the Dirichlet function, what would the upper Darboux sum be? Well, I go through any partition whatsoever. Any partition whatsoever. Since the rationals are dense in the irrationals, the m's are up here at 1, and the little m's are down here at 0, aren't they? So I would be taking the capital M, which is 1, and the lowercase m, which is 0, and I would be multiplying for every one of the elementary rectangles, whatever its width, I could multiply that by 1. So if I add up all these things, I would get 1 for the total width of all the rectangles times 1. So we would then say that the upper Darboux integral of the Dirichlet function is 1. Right? We would say that. What would we say the lower Darboux integral of the Dirichlet function would be? 0. Okay, so those two things exist, but regrettably they're not the same. If they are not the same, the function is not Darboux integral, as it has happened here. Right? And we give up, that's it. Can't do it. Turn the crank didn't work. And remember, we don't know this yet officially. I think we'd like to establish this technically. The Riemann integral and the Darboux integral integrate exactly the same function. So if the Darboux system can't do it, neither can the Riemann system. The Dirichlet function is a famous function that can't be integrated with the Riemann. Hence the Darboux, as we've seen here. Okay? All right. Amanda, is this all making sense? Just check it. All right, that's the Darboux